Okay, this is the lab on the preparation of cupric sulfate solutions, and we're going to walk you through some of that, and we'll show you the experiment. A lot of what we're going to do measuring these, we're going to measure the concentration of these solution uses Beer's law. We're going to use a Spec 20 to do that, and it's because the concentration is directly related to the absorbance. That is, if the absorbance increases, the concentration must have increased. So the law essentially states that those two properties are directly proportional at a particular wavelength. If you vary the wavelength, you're going to vary the absorbance properties. And so A is equal to epsilon VC, where A is an absorbance with no real units. That epsilon is the molar absorptivity, and inverse molarity times its inverse centimeters, where B is the path length of the sample cell in centimeters. Our cells are going to be 1 centimeter in diameter, so that will factor out. And C is the concentration, which will be in molarity. Beer's law plot is going to be a straight line where the absorbance is the y-axis, the concentration is the x-axis. The absorbance will range in values between 0 and 2, where 0 is no absorbance to the light and 2 being full absorbance of the light. And so we're going to look at part A, where we're going to walk through preparing the 0.5 molar cupric sulfate solution. This will be our stock solution for the rest of the experiment. And we'll walk you through making that on the video. Okay, we're going to weigh out our mass of cupric sulfate, and this will be anhydrous cupric sulfate, needed to make about a 0.5 molar solution with 100 milliliters of total volume. You'll want to calculate that out for yourself, but you'll see the approximate value when we weigh it out. And so we're going to put a piece of weighing paper on there. And it's about 0.401 grams, fluctuating just a little bit. But we're going to just tare it, and so we're going to hit the tare button, and then that will zero it out, and we'll weigh out our cupric sulfate. That's a little too much, so we're going to take some away. That's about the right amount, so we'll leave it at that, and then we'll start making our solutions. Okay, now we're going to make our solution in a 100 milliliter volumetric flask, because we're trying to make a 0.5 molar solution of cupric sulfate. And again, we're calculating the concentration based on anhydrous cupric sulfate, because that's the salt we used, as opposed to the pentahydrate. So we need to add that to the flask, and I'm going to use a funnel to make sure I don't make a mess. So here's our previously weighed cupric sulfate, and I'm going to carefully get it up over the funnel, and we're going to drop it in there. And it's okay if it doesn't want to go through the funnel. Depending on the width of the neck, it'll be okay. You tap, 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 it'll go on down. If it doesn't all go, we're going to add the water through this funnel, and we'll wash out the paper as well. So we're adding water now, You can see there's a little bit left in the funnel, which I am washing down, so that is okay. We want to kind of stop there. I want to make sure that I get all of this off the paper, and I want to make sure I get any of this still down in the funnel. So now that I got all my Cupric sulfate down in there, we can see the solution's blue. But I want to get that solid in the solution before I top the flask off, because sometimes the volume of the solution shifts just ever so slightly, and we need to get our fill on this flask to where the bottom meniscus is sitting on that line right where my finger is, right here. And if you don't get it dissolved, once the flask is full, it's harder to mix, and when you do get it dissolved, the volume may shift slightly and mess up your volume measurement. So we're going to go ahead and invert the flask a few times to make sure that goes back in. So we're going to take that, and I've got a cork on it that's tapered glass, and we're going to get that Cupric sulfate to dissolve. And you can swirl the flask a little bit if that helps, but you just need to get that to more or less dissolved before I go about making the rest of the solution. Then what you're going to do is finish filling the flask. And so we can add a little bit more distilled water or deionized water, whatever you have. I'm going to add until I get close to the bottom of the neck of that flask. Now you're getting a little too close for comfort, because again the line is right there at the bottom of the neck. So we're going to add from a squirt bottle, because I can do it much more carefully than just pouring it in. And I can drop wise until the bottom of the meniscus, maybe one or two more drops, is on the line on the flask. Now I need to get that to mix thoroughly, so you invert the flask several times to make sure it mixes and make sure all of that cupric sulfate dissolves. Cupric sulfate is fairly water soluble, so it should go in with no problems. But we're going to invert that until it goes in, and we're going to let it sit for a few minutes to make sure it's been thoroughly mixed. Part B, we're going to make dilutions of that 0.5 molar solution. We're going to have a solution where we didn't add any to that, and that's going to be our blank. The blank doesn't contain any cupric sulfate and be used to calibrate our instrument. In our case, that's just going to be deionized water. And so we're going to add 1, 5, 10, and 15 milliliters. Volumetric flasks are good to 2 decimal places, as well as pipettes that we'll be using to dispense those volumes. And so it should be 10.00. And we're going to dilute it to 50.00. And so so that you get your significant figures right. So we're going to dilute that up in a 50 milliliter volumetric flask. And then, based on measuring our known dilutions, we'll establish a calibration curve. Now, calibration curve is going to be from our best fit line, and so where each of those dots represents an absorbance and concentration of one of our solutions. How much light did it absorb, and what's the concentration? Plot that for some known samples, and then we're going to establish a best fit line through the points. And if you plot in a spreadsheet program, you can get the equation of the line from the spreadsheet program, and you get your y equals mx plus b. Alternately, if you're plotting on paper, plot it on your graphing paper accordingly. But you'll have to kind of read the absorbance and the concentrations off manually. Then you're going to measure an unknown, and you're going to figure out where it is. And so you're going to measure the absorbance of an unknown concentration. So you know the y, and you're going to have to solve for the x using your y equals mx plus b, or by going over to the graph and the y and then down to the x-axis and figuring out what the concentration is. And so we'll measure some of those. Okay, the next step is going to be to prepare our dilutions from our 0.5 molar cupric sulfate. So we're going to do a dilution with 1 milliliter of the cupric sulfate in a 50 milliliter flask and then dilute to the mark. We're going to do it with 5 milliliters of the 0.5 molar cupric sulfate in a 50 milliliter flask and then dilute to the mark. And then we're going to take 15 milliliters of the cupric sulfate to the 50 milliliter flask and dilute to the mark. And so we need to prepare those dilutions, and I'll walk you through one. The rest will work the same, but we'll want to prepare those dilutions. So this is actually a 5 milliliter pipette. Now remember, these volumetric flasks, when you're on the line, are good to 2 decimal places. So that's 100.00, and this one would be 50.00. This is a 5 milliliter pipette, so it would be 5.00 when you're on the line on the neck. So we're going to pipette our solution now. We're going to pull solution in. Do not pull liquid up into the pump, but get it up into the neck. And we want to get that to the line. There's a little roller on the pipette you can use to get it to the line. And we have that pretty much on the line. If we kind of pan up, we can see there's the release valve, and then we can see there's a roller on the pipette. And you use that to get it onto the position. This trigger will allow you to drain the pipette without pulling the pump off. Now we are going to dispense that, so that we're going to squeeze that trigger, and we're dispensing it, or you can just pull the plunger entirely off. But there may be a little bit left in the pipette. That's okay. Once calibrated to the drain, is to drain by gravity, so just touch that to the wall of the flask. Make sure that last drop goes in, but don't try to blow the pipette out. And then we're going to add water to the flask just like we did before, dilute to the mark, except we don't have to worry about draining the solid. Just be more careful because it is a smaller flask. So we're going to come in and add our water. We're getting kind of close. So I'm going to stop adding from a beaker and add from a squirt bottle. That way I can get it exactly on the line. If you pour from a beaker, you're going to overshoot it. So that meniscus is on the line, and then just like before, we're going to cap that, and we're going to invert the flask several times to be sure that it mixes. And it's a good policy to let it sit a few minutes before you actually use it. And so we'll leave that there, and we'll make the other solutions. Now we can see our solutions just a little bit. And you can see this is where I added 1 milliliter, and it's pretty light. And then 5. and then 10, and then 15, and this last one is my original 0.5 molar solution. And so you can see the solution gets darker blue the more concentrated that it is. And that's going to be the premise of what we're going to do next, because darker blue absorbs more light. Therefore, we should be able to determine something about the concentration of the copper in these solutions. Okay, this is a Spec 20, and we're going to measure the absorbance of the cupric sulfate samples that we've prepared, and we've put them into a special container called a cuvette that's designed to have laser light pass through it. So if you look at the instructions, you let it warm up, which we've done. It was warming up while we were getting the experiment going. We're going to set the wavelength by turning this knob right here, and I've set it to a wavelength of 640 nanometers. That's not the maximum absorbance of cupric sulfate in aqueous solution. It's about 780, but we don't want it to absorb too strongly, because absorbance ranges in value between 0 and 2, where 0 means no absorbance and 2 means full absorbance. And if it gets too concentrated, you'll exceed the detection limit of this machine, because once I get full absorbance, I can't measure any increase in concentration past that. So we're coming off of the maximum absorbance so that we can get measurements for our samples. So first, we're going to insert our blank. In our case, since we're just dealing with aqueous solutions of cupric sulfate, it's just distilled water, but nonetheless, we have to blank out our instrument. So we're going to insert that cuvette. Make sure you insert it the same way each time so you get a consistent reading. And then we're going to hit this red button. And you see that that's getting our baseline, and it'll flash, and then it'll eventually zero out our spectrophotometer. It should read 0, meaning that our blank that doesn't have any cupric sulfate in it has an absorbance of 0. So now we've accounted for any refraction of light, anything that happens as that laser goes through that cuvette full of water. And now we should be able to accurately measure our cupric sulfate samples. So we're going to remove the blank, and we're going to add the solution where we only had 1 milliliter of cupric sulfate, so our least concentrated of our solutions. And give that a second to settle out. And we can see we're getting 0.01 as an absorbance. So now we're going to take that out, and we're going to put the one where we added 5 milliliters, and we get 0.16. We're going to take that one out, and we're going to add a cuvette full of the solution where we added 10 milliliters of cupric sulfate. And so we get 0.27. And we're going to take that one out, and we're going to put the one where we added 15 milliliters of cupric sulfate. And we get 0.39. Now if we put the full strength 0.5 molar cupric sulfate in there, so this is the undiluted solution, we get 1.26. Again, all these were measured at 640 nanometers. The amount of absorbance will vary if you change the wavelength. So we're going to take that full one out, and so we're going to establish a calibration curve based on those. That is, we'll get a straight line, and we'll use that for our unknown. So this is an unknown concentration, so based on the knowns, we'll get the unknown, and we find that the absorbance of that unknown is 0.34. And so we're going to set up our line, we'll do our graph, and determine the absorbance based on that 0.34 absorbance. So we're going to make a plot where the concentrations of each of those solutions, when you calculate it for each of those dilutions and the full strength solution, plot that on a graph, and then using the absorbance, the unknown, the absorbance is y, concentration is x, so if I know my y, I can solve for x. And you can either plot that by hand, or depending on your professor's preference, you can plot that in Excel or some other spreadsheet program.